అది అది our one
Today, in the era of globalization, there is no such issue as borders between states of the same nation, said by Fatas Nano. I deem it a great honor to welcome you all to the inaugural function of Nanotechnology Council. Before you are a leader, success is all about growing yourself. When you become a leader, success is all about growing others. Now, I would request Dr. S. Brinda, Sairam Untitled Chapter, Student Branch Counselor of Sairam Engineering College, to address the gathering.
Olivia, the respected CEO of higher institutions, Prakash Muthu, respected principal, Dr. Kurkumaran, respected Dean Academics and Head of the Department, Dr. Raja, Chief Guest of the today, Dr. James Morris, fellow staff members, and my dear ICT student coordinators, and my dear student members. Very good morning. On behalf of Department of ECE and on behalf of ICAs student branch, I take immense pleasure in welcoming you all for this inauguration of Nanotechnology Council. This is the first council we are inaugurating today. Many councils are there in ICT, but this is the first council we are inaugurating. But we have 20+ societies in our student branch. More than 30 societies we have initiated, but this is the first council. And this is one of the most important council in ICT. So we are I am very proud to say that we are inaugurating this Nanotechnology Council today for the benefits of students and faculties, those who are doing research. And if you say the word why we are starting this nanotechnology, nowadays we want everything in a small size. Miniaturization. So miniaturization is the concept expected worldwide nowadays. So how to achieve that miniaturization? Components miniaturization. So if you want any mobile phone or any electronics item, we want that component in compact size. So nanotechnology plays an important role to achieve this miniaturization. And how we are achieving this miniaturization by selecting suitable materials to improve the reliability of the component. So there comes an electronic packaging system. Nanotechnology plays an important role in how to assemble all the components within that given specific area. So we expect nowadays the IC sizes are become larger, but we are integrating all the devices on a chip itself, on chip devices. So nanotechnology plays an important role in electronic packaging system, and so you all know how it plays an important role in our day-to-day life also. In most of the applications, the best thing is mobile phone, and then spacecraft, biomedical applications. When you fabricate devices for biomedical applications, we expect small size devices only. So how to achieve that? So by introducing new materials, nanocomposites kind of materials, we can fabricate the devices. So that comes the technology called nanotechnology. Okay, so selecting the proper material to fabricate the miniature devices is involved in or educate or study the field of nanotechnology. Okay, so to talk more about this packaging, nano packaging, or how to assemble all the components in the specific area. So we have eminent professor from Portland University, Dr. James Morris. He is president of Nanotechnology Council currently. He is holding that post and professor in the Department of Electrical and Computer Science of Portland State University, USA. So I will brief more about nanotechnology. And then if you look at Dr. James is a life fellow of IEEE member. So life fellow means prestigious membership. And he served more than 30 years in this field, nanotechnology field, and he holded many posts as board of governors and treasurer and conferences of vice president conferences, and he authored many books in the field of nanotechnology. So we are happy and honored to have Dr. James Morris as chief guest today to inaugurate our Nanotechnology Council in our college. Thank you, sir. Thank you very much for accepting our invitation and hearty welcome, sir. Sir, hearty welcome, sir. With these few words, I welcome all of you for this inaugural session.
So much, ma'am. Now I will request Radisha Ji, Vice Chairperson of Nanotechnology Council, to give an introduction about the secret of the game.
Professor Emeritus of Electrical and Computer Engineering at Portland State University, Oregon, with PhD and MSc degree in physics from the University of Auckland, and a PhD in electrical design.
இது சார் அது நடந்துட்டு இருக்குது சார்.
He was awarded an honorary doctorate by the Columbia University of Paris in 2015. He is an IEEE Life Fellow and an Electronic Packaging Society Distinguished Lecturer. He has served the ECS in the multiple roles for more than 30 years, including 20 years on the board of Ghana, and period as treasurer and conference leader. He is now equally involved in the IEEE Nanotechnology Council, currently as president and recently as general chair for NMB 2018 and Nanoparticle. He has held multiple visiting positions in universities in New Zealand, UK, Sweden, Finland, Germany, France, China, and USA. He is research and
Madam, mute
focused on electrically conductive substances. The electrical chemistry mechanism continues better nanoparticles and he has edited all 4 or 5 books on electronic packaging, work which has been published in China, and 2 on nanopharmacy. The second edition of the Nanoparticle book was published by the same book in 2008. We welcome you, sir. Thank you, sir. Now the stage is yours.
Can you hear me clearly?
Yes, audible, sir.
Okay, do you want me to share my screen? Okay. Thank you for reminding me. I'm delighted to be here on this occasion of the NTC chapter inauguration. I've been concerned whether you can hear me or not clearly, but anyway, good evening from here or good morning there. I will start my talk on nano packaging. I've been just reviewing my slides and realized that I've missed a few items, but that's why it's selected topics, because the subject is a little bit broad to get through in one talk. So these are the topics that we will go through in sequence. The first will be what is electronics packaging, because if you are interested in nanotechnology, that's probably a new area for you. And then we'll move on to nanoparticles, and then carbon nanotubes and graphene. If I'm running short of time, I will skim through the nanoparticle thin films part, but hopefully we'll be on time. So I'm sure that you all know that nanotechnologies are defined where the dimensions are less than 100 nanometers. This is an arbitrary definition, and it's observed in the breach often. I often see papers saying nanotechnology for this, that, and the other, and the dimensions of interest are several hundred nanometers rather than less than. So this is, as I say, an arbitrary definition. I add another one that the property of interest has to depend on that dimension, nanoscale dimension. So anyway, we'll now look at packaging. And from the history, here we have one of the first packages, if you like, of vacuum tubes. And here the big issue was the glass to metal seal of these contacts, because this is in vacuum, and if that seal broke under thermal cycling, because this all gets hot, then you will lose the vacuum, lose the device's properties. So this is what I consider a first package, but these not the first ones, because the first vacuum tubes, of course, were huge, and this is a mini tube, as they called it. Then we moved on to still vacuum packed, but semiconductor devices. This is, I'm sure that you know, the 741 operational amplifier, and this is one of the first 741 packages. Most of my early work was with these things, dual inline plastic packages for digital operations, resistor transistor logic, transistor logic, and those sorts of things. Here's a cutaway section, and you can see this is the chip here, connections made to the chip. Those wires going out would be normally gold going out to copper leads, and there's all immersed in a epoxy resin or plastic. So then from those days, things moved very, very quickly This is a ceramic rather than plastic here. And then over the next 30 years, Intel basically grabbed the lead, and we ran faster and faster, 6 megahertz to gigahertz, and microns to fractions of micron. So this is basically a factor of 100 in scale. So this is a cutaway of a chip scale package. The idea was you don't want a package that's bigger than the silicon that's inside. And so this is one of the early flip chip packages. These are little solder balls along here, making connections to circuitry, which then go to larger solder balls, ball grid array connections. So this is a little historical scan. So generally, packaging was defined here as a classical picture used by IBM. No one seems to know who originally drew it, but the packaging is defined by IMAPs as everything from the chip to the system. So the wafer is cut up, and these chips are located onto a substrate. This is a ceramic substrate with ball grid array connections. These are pins on a probably also a ceramic layer. And those are then mounted onto circuit boards. I'm trying to find the cursor here. Circuit boards. This was defined by IBM as first level packaging, the chip on a holder. Second level packaging, the design of the circuit board. Third level packaging, the assembly and a motherboard. And then multiple levels beyond that, each level basically scaling by a factor of 10 in size. So this is historical. Nowadays, first of all, packaging is multidisciplinary. So the electrical side looks at transmission line refractions and crosstalk, and signal and power integrity, survival of transients in the system and switching in the system, mechanical for support and encapsulation. Thermal is the big issue always, and is a major challenge now because it, as temperature cycles and goes up and down, the package is stressed and flexes. And you know what happens if you flex a wire backwards and forwards, it breaks. And so the package will do the same. The materials involved, solder is an obvious one. So that's metallurgy, but ceramics and polymers more and more are other materials. So a packaging engineer has to understand all of these things. Nowadays, the issue is to engage in 3D construction. Here, the circuit board is laid out in 2 dimensions. The drive now is through 3 dimensions, because these chips, if they're packaged on through silicon vias, then the connectors are short, so lower inductance, and the signal can travel from chip to chip faster. But now we move into another element, termed more than more, in honor of Moore's law, for microsystem integration, and now known as heterogeneous integration, because it puts all of the different disciplines in a single package. So we can have MEMS, sensor, logic, memory, photodetectors, optical components, RF assemblies, all in the same package. And that's another challenge going forward. So this is 3D integration. And the other one is embedded passives to eliminate discrete resistors and capacitors from the surfaces of a substrate. So moving on to nanoparticles. These are the small topic subtopics we'll go through. So the essential thing was a nanoparticle, and nanosilver has been used to combat infections ever since the Crimean War, and so its properties are very well understood. The essential thing with nanoparticles is that the surface to volume ratio is high. So as you go from this one to this one to this one, if you have the surface area is proportional to R squared and the volume to R cubed, then the ratio will be 1 over R. As R goes down, the surface to volume ratio goes up. That means that the more and more of the particle is made up of surface atoms. Surface atoms, as you will know, are bonded less firmly than in the bulk, and so they're more chemically reactive. And that's the secret to a great many of nanoparticle applications. So one of these has been observed for a long time in 1971 in a transmission microscope is melting point depression. A simple way of looking at this is that a nanoparticle, that surface layer of disordered atoms, is liquid light. In other words, can be regarded as all already liquid. So as the nanoparticle goes down in size, the melting point will go down, as shown. These are actual measurements here, but the overall plot is shown here, standardized for multiple materials. This is the bulk melting point, and as the radius of the particle goes down, the melting point also goes down. But notice that on this plot, to get a 5% reduction, you've got to go down to about 5 nanometers in radius. And so a lot of times people will talk about melting point depression with particles of 100, 200 nanometers. And this is nonsense, because to get a, as I say, a 5% reduction, as this is a rule of thumb, for a melting point going for example, some solder, this can't be right. So go to melt 25 degrees lower than the bulk would be to about this. These are figures for solder. So anyway, melting point depression is something that's well known. These were observed visually. It should be able to get the melting point accurately by electron diffraction when the electron diffraction pattern disappears. But now this is usually done by differential scattering calorimetry. So for nanoparticles, for example, to try and lower the solder melting point is difficult in practice. It's not impossible. I was just thinking of a way that it could be done, but I don't know of anyone doing it. All of the nano solders that you see in the literature, actually we'll get onto a different subject for that. But the nanoparticle from melting point depression doesn't have to be a sphere. It can be a rod. And so a cylinder like this, if the solder is sufficiently thin, this nanometer dimensions this way, then melting point depression could work. And so this is one application that's very interesting. It's using melting point depression to solder wires together. This is solder on the ends at relatively low temperatures. I said that we would come back to the nano solders that are featured in the literature. These are almost all by sintering, and sintering is well studied in the past. It's an exothermic reaction here, but we won't go into that. There's a classical formula here. If this is a neck radius and this is the spherical radius here, defined here, sintering occurs mainly by surface diffusion. There can be a bulk diffusion element to it, but usually surface diffusion. So if we rearrange this equation here, the bonding time between two small particles here can be expressed in this form, where it's proportional to the fourth power of the radius. So if you increase the particle size, then the time for sintering becomes larger and larger very rapidly. And the converse is true. So now sintering is used in creating interconnect patterns on a substrate. The substrate can move, and the jet of nanoparticles, like from a desktop printer, can be gone straight out, or they can be charged and deflected by plates to produce a pattern on the substrate. Here's some examples of sintering. So this is a paste of nanoparticles deposited or printed or whatever. And this is after sintering in an oven, or you can do it by laser heating. The one that's interesting to me is this sequence of events here. This is nanoparticles as printed, and then at some time later, 3 minutes, 10 minutes, and an hour, the nanoparticles have coalesced. The nanoparticles must be protected by a surface coating, because they will react together in whatever container you've got them in, unless they're protected until they're ready to react or to sinter. And here there was a polymer coating on the nanoparticles, and it was dissolved in methadol And so the whole particles would aggregate together. We had a little lab experiment that we ran. Didn't have any controls on it, so there was no really experimental results. But you can get nanoparticles with silver nanoparticles, particularly with coatings that are soluble in alcohol, as here, or water. And so we would have these particles with water-soluble coatings, and at room temperature, it made about 3 minutes before the resistance of an aggregate of these particles printed like this, the resistance would drop dramatically after about 3 minutes as the coatings dissolved away and the nanoparticles sintered at room temperature. So this is obviously an application, but not only is the sintering faster as you increase the temperature, but also the resistance of the final system is lower. This is the same results from a different group. The reason is that the sintering process leaves voids. And since the process of coalescence is diffusion driven, the higher the temperature, the less voids. So this is a sort of a picture of how it works. So this is the problem, is porosity in the films, but you can get rid of that by annealing. So this is the grain size goes up as you heat these resulting film, or you can express it as the relative density is going up. We'll talk briefly about electrically conductive adhesives later on. And based on experience there, probably applying a vacuum to this system would have the same effect of increasing the density and therefore lowering the resistance. So this is a commercial product that's now available. This is a copper ink, which is a suspension of copper nanoparticles. And you take a silicon chip with copper pillar interconnects instead of solder balls, dip it in the ink, raise it up, then lower it onto contacts, and you can have an all copper nanoscale interconnect system. This is copper nanoparticles sintered and a copper contact. So there's no interdiffusion or alloying possible in the system. So this is very stable. So I mentioned electrically conductive adhesives. These divide into isotropic conductive adhesives, where these are typically an epoxy loaded with silver flakes and a little powder, which assists the contacts in the flakes when the material is cured. And so it is cured under temperature and pressure. Maybe you have an epoxy underfill for a flip chip, and then the contacts like this and the silver flakes and epoxy works, joins the two contacts together and gives a low resistance contact. Anisotropic conductive adhesive is actually more often used in practice. Here, there are nanoparticles, well, actually just particles of metal, silver, maybe gold-plated polymer balls, in fact, sometimes. And then the chip is brought down onto this, and under pressure, these particles are trapped here and provide conduction across. These ones are in the epoxy, so they don't have any effect. This is a sort of a picture here. These are metal-coated polymer beads in this case. Non-conductive adhesive is just glue, basically typically a gold-to-gold contact or gold-to-copper contact under load and pressure. And this is what it looks like. We won't worry about this one at all. So for isotropic conductive adhesives, typically if the metal, the silver, which is used because silver flakes, if they oxidize, are conductive. That's the oxide is a degenerate semiconductor. Unlike copper, which would be better, except that the copper oxide is an insulator. So we get lower resistance going from spherical particles to flakes, because a flake has a larger surface to volume ratio, so you get lower resistance for the same amount of silver. So the idea then is, if this surface to volume ratio increase produced this change, then using nanoparticles, the people who did this called it porous powder, should produce a lower resistance again. So this is the idea here. Unfortunately, as you can see, the idea works in principle in terms of resistance for an amount of silver, but the resistance goes up at each step. And so this conducts with less silver, but at a higher resistance. So this was a good idea that didn't work particularly well. But then C.P. Wong at Georgia Tech used the nanoflakes in between nanoparticles in between silver flakes here. They still had a higher resistance because of the contact resistance to the silver nanoparticles, and the mean free path in the nanoparticle was very short, and so on. But then heating them up, if you remove that coating that they came with, they sintered the flakes together, and you got a dramatic reduction in the resistance from going from here to here. This idea is being moved forward, and so you can grow dendrites on silver particles, and these have this sort of shape here so that they will sinter together and form bonds. So this is the thing here with dendrites. Either you can get a given resistance at a smaller concentrate amount of silver, or you can get a lower resistance for a given amount of silver. So for the anisotropic conductive adhesives, a similar thing here. These are the silver particles in this case, not the usual thing for ACAs or anisotropic conductive films, but surface treatment, self-assembled monolayers can act as molecular wires and also provide some protection against oxidation, giving lower resistance and a higher maximum current. And here, these two are contrasted. This one stands, the molecule stands off the surface. Here, it hugs the surface. So this resistance result here is that with this one is actually for this, and the resistance goes up above the control resistance. And you can mix to a positive and negative temperature coefficient of capacitance with nanoparticle dielectrics, and with an appropriate layer thickness given by this formula, you can get theoretically a zero temperature coefficient at the right composition. Works nicely. I think the typical one is barium titanate and barium, I'm sure, strontium titanate. Yeah, I think that's it. Of course, those don't have these nice straight lines, but you can get a point of zero temperature coefficient at a working temperature and very much lowered at temperatures around about. So we come down to the nanoparticle thin films, and just going to check my schedule here. We're a little over time, so I will try and go very quickly here. You can have vacuum deposited thin metal films. When the deposition starts, if something like gold and glass, the atoms deposited will run around on the surface until they find a nucleation point or an existing metal island. And then the islands grow. And this shows a secondary effect where you've got secondary nucleation, where these islands coalesce and leave a gap. Then new islands can form in that gap. And then those coalesce and so on. And finally, you start getting the islands growing together into filaments. The filaments join together and you get a continuous film. So this is gold on glass. These nanoscale islands and nano gaps. The conduction through this film, you can connect with no continuous path by electron tunneling, but there is a charging energy associated with the electrostatic energy to charge an island. And these are like a Coulomb blockade in series. The conduction is characterized by an equation like this. This is showing the same sort of thing, but now instead of transmission and electron microscopy, this is now in an AFM. You can see small islands growing together, and the point here is that this is sputtered aluminum. And as far as I know, this is the only study using sputtered films or aluminum films at very high temperature. I put this in just for extra interest. The reason that the islands are created is that the atoms migrate, as I said, then they form a capture distance. And this diagram here, you could see any atom that lands in here is going to be captured either by either by this island or this island. And then finally, as you can see here, with the coalescence of these islands might coalesce together and leave an open area here where the new island can be created. So due to the diffusion distance, the separation of these islands is approximately constant as the film grows in thickness. This is at different deposition rates, and so effectively at different substrate temperatures. And these are the plots that I said were of this form. So they look like semiconductors and properties. And this is an expression of the electrostatic charging energy. It's the energy to remove an electron from an island of radius r to the next island of distance s away. And so the number of charged islands would be given by a Boltzmann distribution at equilibrium. This was the classical model, but then it's pretty well established now that then there are more charges injected into the film when voltage is applied, and that number swamps this number. And the tunneling is given by a normal tunneling term of this form. So why are we interested? Well, if you have the resistance in an electron tunneling effect between islands, if you pull those islands apart, remember this here is, yes, this exponential term here, A, includes the separation of the islands. So if you pull those islands apart, S increases, S increases, and then the resistance goes up. This is basically a strain gauge. And due to the electrical tunneling, this is S on the slides before, we can have a gauge factor, provided the activation energy is constant, of this form. And so the gauge factor, which is plotted here, as a function of the island separation on the x-axis, is a linear effect. But then the secondary effect of the activation energy starts to affect things, and you get this turnover. So this can be used in a package to monitor thermomechanical stress effects. I should say, well, I may as well use it here. A gauge factor is around 150 on this figure here, which is the strain variation of resistance. Also, the activation energy here in the form of, because that's related to the capacitance, varies with the strain. So this is showing that the activation energy can. Gauge factors up to 300 have been found. This is probably one of the most sensitive strain gauge principles around. This is the opposite effect observed with on the activation energy, and this theoretical study shows that you can have both positive or negative effects on the activation energy depending on island eccentricities and adhesion to the substrate. Another effect is the resistance of the films upon exposure to air. This is gold on glass again. This square root dependence on time is typical of diffusion effects. The model is that the tunneling barrier height increases because the surface metal work function increases as it's covered in oxygen or pretty much any other gas. But there's one combination, palladium and hydrogen. Palladium the work function will also increase, but the additional factor is that the hydrogen will go into the palladium islands and increase the lattice constant, increases the island size, so the gap narrows and the resistance decreases. So here we've got both effects at different temperatures, at low pressures. At low pressure, there's only the surface effect and resistance increases. But as you have a greater concentration of hydrogen, then you get this negative effect. One of the problems with using gas sensors normally in these in particular is being able to separate one gas from another. And this is unique response of all of these sensors to hydrogen. And this can be used because hydrogen is a byproduct of corrosion. This could be used to monitor corrosion in the packaging. So we'll move on to carbon nanotubes, mainly interconnections, but briefly thermal. And carbon nanotubes have been demonstrated here. Resistivity values of the connection ranging from around these values. But the idea here is that you grow a forest of carbon nanotubes on the chip and on the carrier, and you press them together like Velcro. And so these carbon nanotubes contact these carbon nanotubes, and you get an effect like this. IBM had a similar concept for removable or reusable contacts for chip testing. But the contacts, the Velcro, in those cases only would survive a half a dozen cycles, and they had to throw them away. So this was regarded as a failure. But here, of course, once you put the flip chip down, you want it to stay down anyway. So, but carbon nanotubes are not the cure-all for everything that people seem to think at one point. So here is the statement that only long CNT lines can outperform copper. That's because at very short distances, copper is actually a lower resistance effectively. The resistance of the carbon nanotube is independent of length until it gets to a certain point, and then you have secondary effects coming in. So the two results of this is carbon nanotubes are more promising for lines like this, i.e. for power delivery, than for vias where you're looking at for low resistance for signal propagation. But you do get a very much higher maximum current density. But these measurements in the literature, if you look at them, they're all for DC. And for signal applications, this is a very messy slide. I apologize for this, but for high frequency applications, there is another effect which makes them attractive. This is a model here of copper with skin effect and so on this rectangular via. And here, these squares represent a carbon nanotube. I've never actually looked through this to try and understand it, so I won't start now. For the inductance of a connector for a copper wire actually goes down with increasing frequency. But the inductance is not such a problem anyway. But so this is the resistance, the inductance of the copper wire remains essentially the same. But the resistance, due to skin effect, takes off and skyrockets with frequency. And so resistance is the problem with signal interconnects. And so the fact that the carbon nanotube resistance at high frequencies is much less than the copper wire is a potential advantage. Yeah, this is all at the gigahertz range, so it's very high frequency. Okay, so carbon nanotubes also possible on through silicon vias. These are bundles of carbon nanotubes. You can see multiple carbon nanotubes here. At a different scale, these are bundles of carbon nanotubes grown inside vias. You can see the dimensions here. These are about 150 microns deep. And so this is a bunch of these poking out from etched vias. So this demonstrates the viability of carbon nanotubes for in-via connections, through silicon via connections. These are multi-walled nanotubes. There's an earlier result here from Infineon, I believe, where this is a single 15 nanometer carbon nanotube grown in a 35 nanometer via. So that certainly says that in principle, single carbon nanotube interconnects are a feasible, very, very high density interconnect in silicon, through silicon vias. It doesn't mention the problems of contact at the other end and everything else, or mass production. This is a demonstration of feasibility. The other thing with through silicon vias is that the copper via now being used, not extensively, but in some technologies, particularly memory. At a given temperature, here's the copper in the via. You raise the temperature, the copper expands. The silicon also expands inwards. So the copper extrudes out of the via. Sorry. And when it returns to this temperature, the copper is poking out the end with holes down the side to create possible problems, etc. The interesting thing about carbon nanotubes is the thermal coefficient of expansion, particularly in this example, metallic single wall nanotubes. And if you look here at the coefficient of thermal expansion, it goes not only zero at absolute zero, which is not surprising, but it goes negative. And it goes negative, this is 300K here, so it goes negative, which is very much counterintuitive. And the detail varies from armature and zigzag carbon nanotubes and radial versus longitudinal and so on. But the thing is that if you mix this carbon nanotubes in copper, you can reduce the coefficient of thermal expansion. And in fact, a study of ours, if you had aligned single wall carbon nanotubes in a copper via, so they're all running in one direction, a 39% volume carbon nanotube content will exactly match the coefficient of thermal expansion of silicon. So there's no pumping. And also the axial and radial values are slightly different, but you can also get much less pressure on the silicon wafer with the carbon nanotubes in the copper rather than just bare copper. So again, this is carbon nanotube bumps for interconnection for flip chip and so on. The carbon nanotube will resist electron migration and also can be regarded as essentially flexible, so there's a lot of fine lines here. So we can get effectively low electrical migration and stress-free, and also a high thermal conduction. But there is a contact resistance issue. And this one, the electron migration, is creating a problem as we go down in size with solder joints, because the electron migration that we saw in integrated circuit interconnect on chip in the past, now it's rearing its head because basically if you go through the theory, the higher molecular weight of solder and a couple of other properties means that solder will permit electron migration at about 2 orders of magnitude lower current densities than aluminum or other normal IC interconnects. So it's a packaging problem with solder. So carbon nanotubes also possibly will present a solution to the thermal issues, thermal cooling of chips that I mentioned before. Here's the thermal coefficient of conduction for graphite. Remember, graphite is basically lots of layers of graphene, random mixtures of multi-wall nanotubes. This is what is, people currently use graphite for cooling. We can get better by an order of magnitude at 300 K with single wall nanotubes rather than multi-wall. But if you're going to line those single wall nanotubes, look, we're going, well, at least 1.5 orders of magnitude. So this is a possible solution to the thermal problems on packaging. And there was an attempt to do this. These are carbon nanotubes. These are bundles of carbon nanotubes. And these bundles put into and form these channels. So there's lots of carbon nanotubes in here. And then you flow water or air along the channels to cool the chip, which is at the base here. Works well in principle. The problem is inside those bundles, there's no lateral contact between the nanotubes. So you've got very, very good cooling along these edges, but inside the bulk here, there's nothing going on. Now, there's another group have grown carbon nanotubes crossways for linking these carbon nanotubes. So this problem in the original study should be solved, and this should be a viable technology again. So we come to graphene, and I'm 5 minutes later than I wanted to be, but should just finish on time. So graphene, this is a comparison of the thermal coefficient of conduction, coefficient of thermal conduction in various carbon allotropes. So amorphous carbon, not very good. Graphite, this is sort of the standard. This is what has been around for a long time. Graphite grease is used for getting a good thermal match between materials. Diamond-like carbon surprised me because I thought when this was all the rage that it was supposed to be a high property, but not as good as graphite. Polycrystalline diamond, better than diamond-like carbon. Single crystal diamond. This is industrially made diamond. This is gemstone diamond. If you want to go to your friendly neighborhood jeweler and buy your heat sink in the form of gem quality diamond, this is where you are. But carbon nanotubes are way better, and graphene is potentially better still. So this is the interest here is in two-dimensional graphene. Carbon nanotubes are basically one-dimensional. graphene sheets two-dimensional. But this is the thermal, I can't read this, but it's basically thermal conductivity. Graphene here, very, very high for one sheet. So you put on a second sheet, bang, the value drops precipitously. And each other sheet you add drops the effective value. And because if you add layers of graphene, basically you're making graphite. So here's the high quality graphite line and the standard stuff. This is just the same thing for different types of graphene. So this is a problem because you might not get the enough heat flow with one layer of graphene. And if you add a second layer, you're going backwards with this drop in properties. So this graphene is viewed as a potential heat spreader. The problem with heat in semiconductors is it's localized at the device, and the chip is bigger. So if you can have a layer of graphene or something like that to disperse the heat uniformly across the chip, that's a plus. And so this is just more detailed. A material, a composite made of graphene flakes is shown here. And this is not realizing the potential because it's a composite. And these are for carbon nanotubes are increasing diameter here. Details are given here. So this is you can get an increase on those values by compressing the graphene layers, but it's not orders of magnitude. You can have graphene conductors, multi-layer graphene nanoribbon. The models are just like a regular transmission line model for crosstalk and so on. But the idea is if you can have graphene interconnect laterally and through silicon via carbon nanotubes, then you've got a carbon or carbon transmission system here. And so this is an idea that people are trying to make contacts from the graphene to the carbon nanotubes. And I mentioned that if you put multiple layers, then the property of the graphene starts to be lost. But if you put a layer of something like ferric chloride, this is the first material I heard of, but there are other materials that work the same way. That breaks the van der Waals forces between these so that you get the ideal property of this graphene layer and this graphene layer and this graphene layer. So you get effectively the single graphene layers in parallel, which is what you want. And this is the dream. All carbon nano interconnect and devices. I haven't mentioned that you can have carbon nanotube MOSFETs, obviously not MOSFETs, but complementary devices, P-type and N-type. And then with graphene interconnects and carbon nanotube vias, we've got an all graphene, an all carbon structure with no intermetallic interfaces for corrosive effects or anything like that. I think that's a way off, but that's the dream. So I'll finish up there. There's a couple of references here to the key book here is, this is the original in 2008, and there was a second edition came out a few years ago. Actually, most of the things that I've talked about here are not in the books. So as a last thought, what to watch for in the future, I think plasmonic interconnect has a possibility. The problem with, because it doesn't conduct in the bulk of the metal, it conducts in as a surface wave. So there's really no I2R losses. But there are impediments. It's only good for short distances unless you've got some sort of pump, which complicates the issue. But that's one of the things that I think can come along and make a difference. Okay, thank you for your attention. I'm sorry, I'm 5 minutes over time. I decided I was on time and I could include a few things, but I misjudged. I always do. Okay, thank you for your time.
Thank you so much, sir. Student, do you have any queries? Hello, sir. I have a doubt. What is the difference between nanoparticle and nanotube, sir?
I confess that I can't hear you. That was why I was asking if you could hear me clearly, because the sound that I'm getting is very low volume, also with a strong echo, I think, is from the room. So I can't get what you're saying.
Sir, is it audible now? Hello, sir. Is it audible now?
I apologize, I can't understand. Can I suggest as a practical solution that your host collects questions and emails them to me, and I can answer them that way?
Sir, is it audible now?
I can hear that it's a higher volume, but it's still too much echo.
So what is the difference between nanoparticle, nanotubes, and nanofilms, sir?
That I could hear. Okay. Nanoparticles are three-dimensional. The easiest form is to handle is a sphere, and powders are usually spherical particles. Carbon nanotube is two-dimensional. Sorry, one-dimensional because it's basically a wire. And graphene, of course, is a two-dimensional form of a carbon nanotube. I think you asked about a thin film, though, and that is usually a layer, could be a continuous layer for an interconnect, for example, of dimensions typically less than a micron to be regarded as thin film. The ones that I was talking about are layers, or is a layer of nanoparticles on the substrate. So that's a discontinuous thin film.
Thank you. Thank you, sir.
Thank you.
So, what are the potential application of nanotechnology in occupational safety in health, sir?
Occupational safety and health is an area which I include in longer things. If I was giving a course of what they call EHS, environment, health, and safety. So things like inhaling carbon nanotubes, what's that likely to do to your lung? The short answer is that carbon nanotubes might be like asbestos fibers, and coincidentally, my daughter is a lawyer who used to specialize in asbestos cases, and though asbestos problems in the lungs not always damaging. Short fibers, the tissue will grow over them. Long fibers, that's a problem. And the expectation and the early work is carbon nanotubes work the same way. Short sections, the body can tolerate, but long sections are a health hazard. Similarly, there's questions of nanoparticles. Nanoparticles can travel in the body and through the skin. So there's evidence, for example, of particles, ink particles from tattoos being found in, trying to think, I think the spleen. Anyway, one of the body organs. So there's concern about nanoparticles affecting functions within the body. In particular, there was concern about nanoparticles crossing what they call the blood-brain barrier. And I think that's demonstrated that can happen, but I'm not sure that it's ever been a big issue. The biggest environmental issue, as far as at least some years ago, was seen to be silver nanoparticles, because as I mentioned, they're used in health issues to combat infection, but they also grew in usage for socks, for example. There was a period when silver nanoparticle impregnated socks were sold because they didn't, they stopped your feet smelling. And similarly, nanoparticles to be added to dishwashers and washing machines and swimming pools because they're an antibacterial agent. But those sorts of uses, I believe, have been banned because they silver nanoparticles getting into rivers, lakes, and eventually the sea, the antibacterial action is the same thing as they kill the bottom of the food chain in the sea, the microorganisms that other organisms rely on. So they're very bad for the ecology. Now, silver nanoparticles pursuing this still. If you've got an area in the harbor, for example, with a lot of hydrogen sulfide, which is, you can say, is the smelly areas of the harbor, that hydrogen sulfide will react with the silver nanoparticle to perform silver sulfide. Now, silver sulfide is benign. It doesn't have any problems. So in fact, the silver nanoparticles can get basically incorporated in the mud at the bottom of the harbor. So this is a mitigating effect. And before one gets particularly concerned about silver in the sea, and at least some years ago, the density of silver nanoparticles in harbors, I think the particular case that was reported was San Francisco. is not at the same level as when film photography was commonly used. One of the things with digital photography is that you don't have a film and you don't have a developer and so on. And a lot of those photographs basically used silver. And so when digital photography took over, the silver content of harbors started to go down. Then more recently, it started to go up again, but the overall impact is still controversial. So that's environments and health and safety. There are some standards and there are various protocols in place. Users of nanotechnology are legally required to regularly consult various databases and contribute to those databases any of their experiences. There is a legal requirement to do that. And if a company doesn't do that and has a problem, then they're liable not just to fines for not following proper procedures, but they can be required to pay penalty amounts for negligence. So there is a legal framework. I'm not sure how many countries it covers, to take precautions and be aware of the latest information on nanotechnology safety issues. I hope that answers.
Thank you, sir.
Thank you for the
Sir.
question.
Sir, I am Saktish Kumar from Sairam Engineering College, sir. Sir, I have one question, sir.
Sorry, I didn't catch that.
Sir, how far away we are from the mass production commercialization of graphene, sir?
Yeah, you're getting outside my expertise. Graphene you can buy commercially. Now, the nature of what you can buy, I'm not sure about. I couldn't figure out how one could actually put exfoliation, which is the process of having some graphite and then removing the graphite layer by layer till you've only got one layer left of graphene. Couldn't figure out how you could actually automate that. But you can buy graphene flakes. I'm not sure how big the flakes now are. But of course, large area graphene is what people want. And I really don't know where that's at. I think you buy flakes at least in the millimeter to centimeter sizes. But again, I don't know how you would store it and use it. I can't imagine how you pick up a single atomic layer. There must be specialized approaches to that, but I have no experience of that.
Thank you, sir.
It's a great honor to propose the vote of thanks on this memorable occasion. Let me first of all start with the mighty for making today's occasion a resounding success. First and foremost, I thank our chief guest, Dr. James E. Morris, Dr. Honoris Causa, Professor Emeritus, Department of Electrical and Computer Engineering, Portland State University, Portland, United States ICAs Nanotechnology Council President 2021, who despite his busy schedule has found time to raise the occasion. Thank you, sir, and I express my heartfelt thanks to our CEO, Sri Sairam, Principal Dr. E. Porkumaran, our HOD in Academics, Dr. Raja, for their valuable support towards this occasion. I would like to extend my thanks to our ICT captain and ICT SP counselor, Dr. S. Punda. I wish to thank the society members, R.K. Subramani, IEEE NDC Chair, Radisha G, IEEE NDC Vice Chair, Ritik Roshan B, IEEE NDC Secretary, Jana Sudarshan, IEEE NDC Headmaster, Ramna Kishan, IEEE NDC Treasurer, Keertana, IEEE NDC Technical and Executive, Arun T, IEEE NDC who worked hard to ensure that this occasion become a memorable success. Last but not least, I wish to thank staff and friends for their cooperation in making this day a grand success. Once again, I thank you all for your attention.
Hello, sir. So this is Aditya
Hello.
here, sir. Sir, thank you so much for joining for the day, sir. It was a great pleasure having you virtually in the campus.
Thank you for inviting me. I enjoyed it. I'm sorry for the sound difficulties, but I think we got over them to have some questions, which is a good thing. So I will leave now, and thank you very much again for having me.
So thank you, sir. Thank you very much for your wonderful
Okay.
presentation. We will connect
Thank
in
you.
future also, sir.
Okay. Thank you. Bye.
Thank you very much, sir. Thank you. Thank you. Bye, sir. Bye, bye.